Hello and welcome. In this video, I want to take a look at the notion of independence of path and see how that tells us about whether or not a vector field is conservative or not. So, we'll give first a definition of what I mean by independent of path. Let F be a vector field with domain D. Now, I'm being a little cagey here and not saying how many variables I'm talking about, but this doesn't matter, 2 dimensions or 3 dimensions or more. It's the same idea here. So if F is a vector field in domain D, then the vector field is called independent of path if the line integral of F along curve C1 is equal to the line integral of F along C2 for any two paths, C1 and C2, with the same start and end points. Now I want to distinguish here, this does not mean that C1 is a loop and C2 is a loop. We mean that there's 2 points. There's a start point and there's an end point, and C1 does one path to get there and C2 does a different path to get there. Okay, or maybe the same, but anyway, they could be 2 different paths as long as they start in one point and they end in the other point. Right? And we're saying that if you have a vector field for which the path doesn't matter, then that's what's called independent of path. And here's the theorem of why we want to talk about it here. It says if F is a vector field on an open connected set D, then F is conservative if and only if it's independent of path. So conservative fields are independent of path, and fields that are independent of path are conservative. Okay. So here's my proof. So this is an if and only if statement, so I have to prove it in both directions. I'm going to do the easy way first. So first let's assume that F is a conservative field and show that it's independent of path, and then when we're done with that, we'll turn it around, go the other way. So I have assumed that F is conservative on an open connected domain D. We want to show that it is independent of path. Okay. So let C1 and C2 be any two paths on D that start and end in the same places. Right? So they both start here, they both end there. Okay. That is, suppose you've got two parameterizations, R1 of T, with T between A1 and B1, being a parametric representation for curve C1, and you've got R2 with T between A2 and B2, and this is the parametric representation for C2, with R1 of A1 equal to R2 of A2, and R1 of B1 equal to R2 of B2. Now, see, I'm being a little careful here, is that it's not that the T values have to be the same, it's that the first T value you put in for R1, it should end up mapping you to a point which is the same place that the first T value that you plug into R2 sends you to. Right? Likewise, in the end, the last T value for R1 should be sending you to the same place as the last T value of R2. So the A1 and B1, so the A1 and A2 might be different T values, but they're the start of their respective parameterizations, and B1 and B2 again are the ends of theirs. Okay. Since F is conservative, we know that there has to exist what we call a potential function, a function little f, such that the gradient of little f is capital F. Then the fundamental theorem of line integral tells us that the line integral along C1 of f dr is, actually I should say f dotted with dr, is the potential function evaluated at the endpoint minus the potential function evaluated at the start point. Right? It only depends on the endpoints. This is the whole point here, that once you can get it to this point, then you say, oh, well, plugging in R1 of B1 is exactly the same as plugging in R2 of B2, because right over here, they're the same. And likewise, plugging in R1 of A1 is the same as plugging in R2 of A2, because again, they are the same. But this difference is what you would get if you integrated the vector field F along C2. Right? And so if it's conservative, the integral only depends on the endpoints, and if the endpoints are the same for both curves, well, you get the same value. Okay, so conservative implies independent of path. Now we have the more challenging part of it. Now let's assume that F is independent of path on an open connected region D. We will show that it is conservative by actually producing the potential function. And we'll do this proof here in R2, but you'll be able to see that the continuation into R3 is just one more step, very much like the 2 steps that we're going to do here. So in our domain D, let's pick one point, which we're going to call our base point. It's going to be a fixed point. I'm going to label it x0, y0. And then pick any other point, xy, in the space, and I'm going to define a function, little f, on that xy. Okay. And C will be a path from x0, y0 to xy. Now, I know that such a path exists because D is connected. The region that I'm in is connected, which means that between any 2 points, there's a path. Right? There may be more than one path, but there's at least one. Okay, so there's such a thing does exist, and I'm going to define f of xy to equal the line integral along C of f dotted with dr. Now, at first glance, this may seem like it's not well defined, because if you picked one path and I picked a different path, we might get different line integrals. But if we're assuming that f is independent of path, then it doesn't matter which path you pick. If you start at x0, y0, and you end at xy, you're going to get one particular value. Now, if you change that ending point, you may get a different value. But for a fixed starting point, you tell me what xy you want, I can define this function f to be the line integral along any curve that starts at x0 and ends at xy, integral of the vector field along that curve. Okay. What I want to show now is that this function is in fact the potential function. And this is actually kind of cool to me in that if you think about the fundamental theorem of calculus part 1, if you've got some continuous function, the first part of the fundamental theorem of calculus says it has an integral, it has an antiderivative, and here's what the antiderivative is. It's the integral from some fixed point to x of f of t dt, right? That is, you make your variable the upper limit. And what are we doing here is we're making our variable xy be the endpoint of a line integral. So it's essentially the upper limit of the integral from x0, y0 to xy. And so there's a really nice parallel here as to what we're doing with two variables as to what we did for the fundamental theorem back in Calc 2. Okay, so we want to show that the gradient of this thing is capital F here. So here's the path I actually want to choose. Okay, because D is an open set, the point xy is not on the edge, because open sets don't have any of their boundary points in the set. So xy is in the interior, which means there's a little disk around it, a little circle that is completely contained in D. What this allows me to do is to pick another point which is directly horizontally still within D, but beside that point. So here's my point xy, and I want to move over. I want to change just the x coordinate to what I'm going to call a comma y. So the same y coordinate as the xy I'm going to, but it's got a slightly smaller x value. Okay? And I know I can do that because D is an open set. Okay. Now I want to make a curve from x0, y0 to this point a comma y, which I also know I can do because both the points are in D and D is connected, so there's a path there. And then I can just do the straight line path from a y to xy because I know that that whole disk is in D, and so I can just draw the line over. Okay, so the curve that I want is the combination of C1 and C2. Okay, so I'm going to use this C right here as the combination of those two. Okay, this path exists because D is open and connected. So now the function looks like, actually let's leave that picture on there. Function looks like this, which I can rewrite as this. Now, I'm trying to prove that the gradient of this function is equal to capital F. Okay? So the gradient is, first component is the partial with respect to x, and the second component is partial with respect to y. So I'm going to take the partial with respect to x and see what I get. Okay? Before I do, I should say I'm going to parameterize this second part of the curve this way. It's just t comma y, where t goes from a to x, right? So this is just, t is just changing the x coordinate starting at a and ending at x. So the partial with respect to x is, well, it's f is a sum of two things. So take the partial of the first thing plus the partial of the second thing. I claim that this first part is a constant with respect to x, right? Certainly the endpoint is, the starting point is constant, and the second point, well, the second point depends on y, but I'm taking a partial with respect to x. And when you're taking a partial with respect to x, you treat y as a constant. So this is a line integral along a curve that starts and ends at fixed points. So the derivative is 0. Partial derivative with respect to x is 0 on this first one. That's that 0. And then I'm still needing to take the partial over the second one. Okay. Now let's actually do that using the parameterization that we had. So the way you do this is f evaluated at points along the curve, dotted with the derivative vector for the parameterization, dt. This is integrated from a to x. And then I'm going to take the partial derivative of that when I'm done, right? So plugging stuff in here, f of r of t is p of r of t, comma q of r of t, and that r prime of t, I can actually calculate this because I know the parameterization is t comma y. And when we say r prime, t is the variable here, so I'm taking the derivative with respect to t, which is 1, 0, right? Y is constant along that path. And so the derivative vector there is 1, 0, and dt. Take the dot product, you just get p of t, sorry, r of t is this parameterization. So I've got r of t being plugged into p, and I've got r of t being plugged into q, and r of t is just t comma y. But now look at what I have. I've got the derivative with respect to x of the integral from a to x of p of t comma y dt. This is the fundamental theorem of calculus part 2. No, part 1, that says the derivative of this integral is just p of x comma y. That is, you just replace the t with an x, and that's what the derivative is. If you find an antiderivative and you take the derivative, you go back to where you started from, right? Except that you plugged an x in instead of t. So what have we shown? We've shown that the partial derivative of this function, defined this way, with respect to x, is the first component of f. Now we can do the same thing again to find f of y, but this time we're going to choose a different curve. It's independent of curve, right? So you can choose whichever one you want. And so to do p of y, take the partial with respect to y, I'm going to choose a point just below here. So again, because this is an open set, there around the point xy, you've got a whole little disk of points that are completely in D, so I can drop down from xy just a little bit, and I know I've got a point that's still in D, and I know the whole straight line path in between is still in D, and so I'm going to take a curve from x0, y0 to that point x comma a, which I know exists because it's D is a connected set, so there's a path between any 2 points in there. And then, so the C that I'm going to do is all the way from here, do C1, then do C2, and you can do the same thing, take the partial with respect to y. The derivative of the first part here is 0 because this is a constant, and then you do the last part and you find you get Q of xy. And so the gradient of f is p comma q, which is capital F, which is what we wanted, so we found the potential function. And perhaps you can see that if you were doing this in 3 dimensions, you'd have to do this again to do partial of z, but this time you would, in xyz space, you would say take a point just below it in the xyz space and do the whole thing again, and you would get the same result. Okay, so this is just amazing to me because we're essentially doing a multivariable version of the fundamental theorem of calculus to get this antiderivative. And we can do this only because the function is independent of path and the set that we're working in is open and connected. Okay. So if you have a function defined, a vector field defined on a open connected set, then it is conservative if and only if it's independent of path. That's actually a stronger theorem than the one about the mixed partials, because the mixed partials required the domain to be simply connected. Right? This works even if it's just connected. You could have a hole in the middle, and if it's path independent, then it's conservative. Right? Which leads me to one more theorem and one example here. If f is a conservative vector field on an open connected domain D, then for any closed curve in D, you have the line integral along the closed curve. That should be a capital F of D r is equal to 0. Yeah, like that. Remember, if it's a conservative vector field, then the line integral just depends on the endpoints. And if you've got a closed curve, the closed curve means you start and end in the same place. You've got a loop. And granted, it may do all sorts of crazy things, but you start and end in the same place. So the integral along that curve is 0, because the function value at the beginning and the function value at the end are the same because you're in the same place. Okay? This is actually why this is called a conservative field. This matches like potential functions for gravity and whatnot, that you're conserving energy, or you're conserving momentum, or you're conserving something, that as you move along the curve, work is being done. But then when you come back to where you started from, you might have had positive work done and you might have had negative work done, but you haven't gained any energy. You're not going faster when you go back than where you started from. You get back with the same amount of energy you started with. Okay? Conservative vector fields, they conserve something. They conserve the potential. You get back to the same potential where you were to start with when you finish that loop. Okay, which then leads me to an example that we had in a previous video where this vector field right here, y over x squared plus y squared comma negative x over x squared plus y squared, we saw that this satisfied the mixed partial thing. So the partial of p with respect to y was equal to the partial of q with respect to x, but yet I'm claiming it's not conservative. Okay, now the theorem that we had before didn't apply because the region that this is defined on is the whole plane except the origin, which, because you accept the origin, you now have a tiny little hole in the middle and it's not simply connected. And so the theorem didn't apply. And this is one of the reasons why it doesn't apply, because when what I'm going to do is I'm going to show it's not conservative by doing a line integral along a closed curve, which should be 0 if it is conservative, but it's not going to be 0, right? So the closed curve that I'm going to do is a circle. I'm calling it sine t comma cos t for t equals 0 to 2 pi. So this is actually starting up at up on the y and going clockwise around once the unit circle. Okay. So it starts and ends up at the point 0, 1, right? 1 up on the y-axis. So if this is the parameterization sine t cos t, then the derivative would be cos t minus sine t. Now looking at the line integral along that curve of this vector function, I'm going to do it by the p dx plus q dy method. So there's the p, and the dx is the cosine t, which is right there, and the dy, no, and the q is that, and the dy is the minus sine t, right? Now I'll substitute all those x's and y's with sines and cosines that we get from the parameterization here. So the y turns into a cosine, and the x turns into a sine. Both of these denominators turn out to be, and I've also replaced this from, rather than integrating over c, I'm writing it as the integral from 0 to 2 pi, because everything now is in terms of t, and the integral is dt, so my limits of integration are in t's. The denominators here are both sine squared t plus cosine squared t, which is 1, so those go away. So this is cosine t times cosine t, that's that cosine squared t, minus sine t times minus sine t is positive sine squared t, right? Cosine squared t plus sine squared t is again 1, and so I'm integrating 1 dt from 0 to 2 pi, which is just 2 pi. Notice that is not equal to 0. So you integrated all the way around this curve, and you didn't get back to 0. Not conservative. This is not a conservative field. Notice that as my integral did actually go around the bad point. It went around the point that the vector field's not defined, right? And so that that particular loop was a bad one, and it did not give me 0, and this is not conservative. All right, there you go. I think we have one more video to do for this section, and we will be looking at just how do you, in general, find potential functions once you know that a vector field is conservative. So anyway, enjoy.